Hello, my name is Javier Salvador Guerrero, and I'm going to talk about frequent hypercyclic behavior of some non-convolution operators on H of Cn, being this the space of entire functions in one or several variables. First of all, I want to thank to the organizer for organizing this seminar, for the invitation, and of course for giving me the opportunity to present our result in this international congress. This presentation talks about a joint work with Alexei from the University of Rostov and Fernando León Saavedra from the University of Cádiz, and it is related with operator theory. As we can see, this material is related with analysis. The concepts of hypercyclicity and frequent hypercyclicity are present on the development of operator theory. The idea of this work is to try to understand how these concepts are linked with other analysis results in order to answer a question posed by Santiago Muro and coworkers, establishing a characterization theorem in an easy way so everyone here can understand it. So, okay, let me talk about the structure of the talk. Firstly, as an introduction, we will analyze some basic definitions in operator theory. For instance, we will introduce the definition of hypercyclic operator, as well as the first examples of these operators that appear in history. Then we will define frequently hypercyclic operators. These operators have been studied in one and several complex variables, but we will focus our talk on operators in several complex variables that act as a translation plus as a differentiation in one of their variables. Next, we will recall some results that are essential for main theorem. We will talk about the Cauchy integral formula, and with this formula we will obtain the supremum of the differentiation operator. Then we will see a result obtained by Eva Collin about polynomially convex sets and the Oka-Weil theorem. This theorem let us approximate functions by polynomials. We will also see a separation lemma useful for constructing a frequently hypercyclic function. To make the calculus easier for the reader, we will state a proposition to reformulate the problem in a different way. Finally, once we have established these definitions, we will state our main result, answering a question posed by Santiago Muro in their work, as I said before. Okay, so first of all, let me describe what is an hypercyclic operator. Well, if we have T, a continuous linear operator acting on H of Cn with n greater equal than 1, then the orbit under T of function f in H of Cn is the set that appears in the screen, this set over here. So the operator T is hypercyclic if there exists a function whose orbit is dense in H of Cn. So, for example, if we consider the tent map, this is the operator T defined by 2x for x between 0 and a half, and 2 minus 2x for x between 1/2 and 1. We can see that applying the operator T several times, we obtain like more triangles in the graph. As you can see, this is the graph of T, this is the graph of T of x, and this is the graph of T of x. So we are obtaining like more triangles. So for example, if we consider x equal to p quarters, this is like 0.78 or approximation, that's approximation, we can see that T of x is approximately 0.5. But if we consider t of x, we have that t of p quarter is approximately 0.8, but t of x is approximately 0.2. So if we consider the whole orbit of this number, p quarters, we will obtain a dense subset of 0, 1. This is the closure of the orbit p quarters is 0, 1, 0, 1. So in other words, T is hypercyclic. Well, the first examples of hypercyclic operators were discovered by George David Birkhoff and MacLane. Birkhoff's finding states that the translation operator, defined by this operator over here, T of H of Z is equal to H of 1 plus Z, is hypercyclic. Similarly, MacLane discovery indicates that the differentiation operator on H of Z, defined by D of H of Z is the differential of H of Z, is hypercyclic. Later, Godefroy and Shapiro unified and extended both results by proving that every continuous linear operator that commutes with translations and it is not a multiple of the identity is hypercyclic. These operators are referred as non-trivial convolution operators. Well, another definition that emerged in linear dynamics is the one we have here, the frequently hypercyclic operator. So we say that an operator T acting on H of Cn is frequently hypercyclic if there exists some function such that for any non-empty open subset U, this set over here has positive lower density. This limit is greater than 0. Okay. Well, so Santiago Muro and coworkers proved that the operator, this operator, T lambda B of f of z, the differentiation of f acting on lambda z plus b, are frequently hypercyclic when b is equal to 0 and the modulus of lambda is greater equal than 1. And they posed the question of whether they are frequently hypercyclic for any b. That question was recently answered from a broad context by Ikram Ben Said et al. One important result used to get frequently hypercyclic operator is the frequent hypercyclicity criterion. And we have it over here. So if we let x to be a separable f space and t a continuous linear operator on x, we assume that there exists a dense subset x0 of x and a mapping S such that for every x we have these two things over here, two properties. First, the series Tn and Sn converge unconditionally, and second, the equality Tn of Sn of x equal to x holds. Then, if we have that thing, T is frequently hypercyclic. So Santiago Muro and coworkers used the results of Oron and Marcuse as a basis for studying the analogous operators on one several complex variable. On several complex variables, not one. Specifically, they studied operators of the following form. T of alpha lambda b equal to d raised to alpha. Alpha is a multi-index with d the differentiation operator of f of lambda 1 z1 lambda n zn plus b, where lambda and b are vectors in some variables, several variables, and These operators has different properties depending on the variable we are considering. The frequent hypercyclicity of this operator was not fully solved, especially when there exists an I such that bi is not equal to 0 and lambda I is equal to 1. So to answer this question over here, if the operator is frequently hypercyclic, we will state these results to help us to answer this question. So we are going to state the Cauchy integral formula, a result obtained by Eva Collin, the theorem, the Oka-Weil theorem, a separation lemma, and a proposition to reformulate the problem. Okay. You may be asking, why would you state that results? We do it because although the results shown by Muro et al. Are based in sufficient conditions to satisfy the frequent hypercyclic criterion, is it not clear how to apply it in such a case? That is because in that case, when there exists some lambda with modulus less than 1, we cannot ensure the unconditional convergence of the series of the inverse of the operator, because it will have a product of constant with modulus greater than 1. However, we demonstrate an alternative constructive method based on approximation theorems in several complex variables that works well. One of the main difficulties about applying constructive methods is the manifestation of hard calculus, but they can be simplified in order to use approximation results easily. That's why with the last proposition, we consider an operator that is similar to this operator over here, and which is easier to use. This let us simplify the calculus as we desired significantly. Specifically, when we do the computation repeatedly, using the integral formula, we observe that there appears a product of disjoint open convex sets that let us apply clearly the approximation result obtained by Eva Collin. So now we are going to show the Cauchy integral formula. And this says that if we let d raised to alpha be the differentiation operator defined on h of Cn with alpha a multi-index, if we suppose that C is a simple closed curve oriented counterclockwise and F is analytic on and inside C, then for all set, we have this formula over here, the Cauchy formula. So as a consequence, the supremum of d raised to alpha of F can be estimated over a set of the form a product of open balls with center Z and radius R, some radius. Hence, there exist positive real numbers delta 1, delta n, so that we can get the inequality over here. As we said before, the demonstration of the main result is based on a constructive method to find a frequently hypercyclic function. In order to construct it, we apply the result obtained by Eva Collin and the Oka-Weil theorem. So the first one says that if we have K1 and K2 disjoint compact convex sets, then the union of these sets is polynomially convex. And the Oka-Weil theorem states that if we let K be a compact polynomially convex set in Cn, then for every function holomorphic in some neighborhood of K, we can find a sequence of polynomials in Z1 sin n with the polynomials converging to F, to the function F. Well, in order to prove that the function constructed is frequently hypercyclic, we need to consider some sets which are a partition of n, the natural numbers. So We do it with a strong separation property and non-zero density. So this is possible thanks to the next lemma. So the separation lemma shows that there exist pairwise disjoint subsets of positive lower density such that for any number in one of the sets and other number in other sets that are not equal, we have this inequality over here and this one, n is greater equal than v. So, as we said before, we could simplify the calculus by reformulating our problem. So in the next proposition, we show that the operator considered by Santiago Muro and coworkers is similar to the operator on the form m, v1, v2, v3, v4, where m is equal to a product of constants, so it's a constant with alpha the multi-index. v1 is the translation operator plus as a differentiation in the first variables. v2 is the identity operator plus the differentiation in the second part of the variables. v3 is the dilation operator plus the differentiation operator with modulus of lambda less equal than 1. And in the first part of the operator, in the last variables, we have the dilation operator plus a differentiation operator with modulus of lambda greater than 1. So we have this aggregation because depending of the value of lambda, alpha and b, the operator act in different ways. So first of all, we move the variables where the operator acts a translation plus a differentiation to the first place. Then we choose the variables where lambda and b are equal to 1 and 0, and we move it to the second part. In the last variables, we reorganize them in order to have first the ones with modulus of lambda less equal to 1, and in the last part, the ones with the modulus of lambda greater than 1. In this way, we consider the operator in separate variables, thus getting a better handling of the calculations, making them simpler. And as a reader, it's easier to see how it's acting the operator in all the different variables. We can do this reformulation because, in this case, the operator acts separately on each variable. So, all this together will let us state our main theorem. So we have this main theorem over here. And if we let T alpha lambda B be the operator on H of Cn, defined as the one defined by Muro, where alpha is not equal to 0 and phi is this function over here. And if we have some I where Vi is not equal to 0 and lambda I is equal to 1, then T is frequently hypercyclic. Thus, we have been able to fully characterize when the operator is frequently hypercyclic, using a constructive but simple method. So in the last part, we will see, I'm going to say that the material used for the work is this one over here. And thank you very much for your attention.